This procedure involves determining the material of the bolt and how it was manufactured. The initial steps are observation. A shiny hard surface suggests this is a metal bolt, and placing a magnet against it identifies it as metallic. Given the instruction, this is a cheap bolt, the cheapest magnetic metal on Earth would be the most abundant, and that is iron. Consequently, it can be presumed this bolt is made of steel, an alloy of iron and carbon. To prove the presumption, a form of reverse engineering investigation is performed. This involves cutting the bolt in half and embedding it in resin so the surface can be ground, polished, and etched to reveal the grain structure. To view the specimen, it is placed on the platen, ensuring there is enough space between the magnification lens and the platen for the specimen to slot between the two without crashing into the lens. The light source from the microscope is located onto the central area of the bolt. Starting with the ×5 magnification lens, the coarse and fine focus dials are used to observe a clear view of the bolt. At ×5 magnification, it is difficult to determine grains and their shapes. At ×10 magnification, the different shapes of the grain are clearer and the lines around them are the grain boundaries. This image of dark and light grains is characteristic of steel, particularly low carbon steel, because of the density of dark and light grains that can be observed. At 50 times magnification, perlites are visible. These are made of dark and light material. The two shades are the two phases. At 100 times magnification, the detail of the phases can be interrogated. The light phase is the ferrite phase, consisting of tiny bits of carbon. The dark phase is the cementite phase. This is what gives steel its high strength. Therefore, more cementite means more strength. To increase the cementite, more carbon is added. Cementite is a compound of iron and carbon, resulting in the molecular structure of iron 3 carbon. At 0.8% carbon, all grains become perlite. Beyond 0.8%, the perlite grains are surrounded by cementite on the boundaries. More than 2% carbon results in cast iron. The carbon is added as graphite in molten iron. Utilizing the X and Y dials, the specimen is maneuvered to the thread boundary of the bolt. At ×5 magnification, note the different densities of dark grains towards the center of the bolt versus the density of dark grains towards the thread boundary. The grains at the thread boundary don't display cut marks through the grain, but a compressed shape, which indicates this bolt was not machined. Instead, the grains at the thread boundary are elongated, following the thread profile, evidencing compression. Additionally, at the tip of the thread boundary, crack propagation and dimension instability can be observed. This is more likely to occur where heat treatment has occurred, and it is difficult to maintain close dimensional specifications with heat expansion and contraction. A cost-effective way to manufacture a high volume of bolts is compressive rolling. This process involves two rollers with a die on the surface, and a rod of material passes between them to have the shape compressed into it. This manufacturing method explains the shape of the grains at the thread boundary. The lack of dark grains at the thread boundary is due to the carbon being more reactive with the oxygen in the air, and it will bind to form carbon dioxide in preference to the molecular bond with iron. This reaction is more likely when heat has been applied to the material, adding energy to the reaction for it to take place, and annealing will require reduced forces for shaping to occur. Hence, the degree of light and dark grains present throughout the bolt means this is a mild steel because of the low carbon content, and the manufacturing method is hot thread rolling.